Welcome to our training series on Intel's next-generation firmware initiative, the Universal Scalable Firmware, USF. For this session we will dive a bit deeper into the configuration data interfacing with both the scalable Intel FSP and the platform orchestration layer or bootloader. One of the most important features of the USF is having the capability to have customizable configurations based on a platform and/or customer's needs. The configuration region is specified as part of the Intel FSP spec and is a data structure called the Updatable Product Data, UPD, containing default parameters for FSP initialization. This overview will discuss the characteristics of the configuration data. Recall in the Intel FSP overview, these are the contents of the Intel FSP package after it is downloaded. Now, let's just study the configuration region. Each FSP module contains a configurable data region, which can be used by the FSP during initialization. This UPD has default values that were validated with a reference platform. However, UPD parameters can be statically customized using a separate configuration tool by changing the values in the boot setting file, BSF. Also, the POL bootloader plays a role, if desired, by the platform developer to make the configuration data dynamically updatable. This option is available to make the configuration UPD flexible according to OEMs and other platform product producers. This slide shows more details on the layout of the FD-FSP binary file as similarly shown in the Scalable Intel FSP overview, but now we're highlighting the configuration sections of the firmware volumes. Also, as part of the downloaded Intel FSP package, there are corresponding H files for each of the firmware volumes, FSPT, FSPM, and FSPS with definitions of the configuration data. The configuration data can be runtime. In this case, the bootloader is going to consume these H files as part of the build process. Thus, the bootloader knows the layout of the configuration data for each of the FSP modules. The bootloader can manipulate the configuration data dynamically before calling into the FSP module entry points. Then there is also the build time or static configuration data. This means the data values are going to be manipulated before the build of the bootloader. There are tools for changing the default values of the configuration data for each FSP module. One is the binary configuration tool or the open source YAML tool. Both will consume the BSF file that is part of the downloaded Intel FSP package. Each FSP firmware volume module has its own configuration layout. This slide is a review from the Intel FSP overview but now is focusing on the configuration data. The diagram on the left shows a pseudo layout of one of the FSP firmware volumes with a firmware volume header and then divided up into different sections showing multiple modules or files. The first file within a FSP firmware volume, shown in the middlemost diagram, must be the FSP info header file. Shown on the right is the FSP info header. Each FSP info header has the exact same layout for each firmware volume of the FSP FD binary. In addition, each firmware volume has its own layout of the configuration data UPD. The details of the layout is part of the FSP integration guide and also detailed in each of the H files that are part of the FSP package in the FSP family include directory. Now let's look at some examples of tools to change defaults for the configuration data at build time. There is currently 2 FSP configuration tools available. Both utilities can be used to change configuration settings embedded in an Intel FSP binary to customize the static UPD configuration parameters. The YAML UPD configuration editor is an open-source Ontiano core that interfaces with the EDK2 build specification files, creating a YAML file for the change descriptions. The binary configuration tool is closed source and uses a boot setting file BSF file for its change descriptions. If you're already familiar with FSP configuration today, the tool to configure FSP parameter is Binary Configuration Tool, BCT. Currently this tool is closed-sourced with installers only. More information about BCT can be found at the GitHub location. So why do we like YAML? If you're in DevOps, you're probably already familiar with YAML. The declarations required to build the configuration data blobs and the header files are provided in a configuration description file. This file uses the YAML syntax. What is YAML? YAML is a data serialization language designed to be human-friendly and work well with modern programming languages. It is made from list of key and value pairs and is a superset of JSON. It has a very long history with many support tools and libraries available. Slim Bootloader is already YAML as its single configuration source. The snapshot shown provides a quick comparison between BSF format and YAML. From here, we can see that YAML is easier to read, parse, and modify. Intel recently added a configuration editor in their EDK2 repository that can allow YAML format configuration of FSP, and some of the features of the config editor are listed on the left. It is open source and Python-based, with a very simple user interface and command line interface. It is backward compatible with previous BSF and allows patching FSP UPD or the bootloader consisting those UPDs. Not only that, this tool also provides a handy search function to let users query the firmware parameters and provide mechanisms to keep track of the changes. On the right, the repository of the Intel FSP is shown with the various SoC platforms now supported for open source. Each of these SoC platforms will have a BSF that can be used with the YAML config editor. So how does the YAML configuration editor work? The BIOS or bootloader would use the Intel FSP for SoC initialization. Consumers of FSP would then configure the FSP parameters to get the SoC initialized as intended. On the right, the menu from the YAML config editor is shown. This, or a similar menu is displayed, and users would have a user-friendly GUI to easily change the configuration. For example, if it is desired to enable or disable a setting, there is a pull-down menu with the item on the right to select either enable or disable. The following few slides will showcase some steps and capabilities of the YAML configuration editor. This particular slide shows the very simple steps to check out and execute the config editor. Shown on the right is what the config editor looks like in the GUI, and shows the functionalities that it currently supports. When invoking the YAML config editor, either a YAML file or a BSF file is required that describes the FSP parameters. The BSF file is for backwards compatibility. This slide shows an example of opening a source BSF file and then getting loaded into the configuration editor tool. When a BSF file is loaded, the config editor automatically generates a YAML file and renders it directly. In subsequent changes, users can use the generated YAML files. This shows how a YAML file would be generated when a BSF file is loaded in Configuration Editor. If users are interested in converting BSF into YAML directly during the BIOS build process, there is an open source utility available that does specifically that. This tool is a Python script called fspdsc bsf2 YAML. The YAML config editor also has an integrated search function. This allows users to quickly find firmware parameters among the hundreds of FSP options. Shown here is an example of searching on the keyword debug. Then the config editor will display all the subsystems on the left that contain the keyword debug. This tool also provides a way to manage changes using a concept of a delta file. When a user changes a setting, the delta file can be saved and loaded to also take effect in the future. The configuration changes can be saved as just the config changes or the full configuration data of the delta file. The default type of the delta saved file is a simple text file. So, upon saving two different full configuration delta files, a simple diff utility tool can be used to show the differences. This example is showing that the values for DCI DBC mode and DCI mod PHY power gate are different for the two different saved configurations. If a binary is patched, and users could not keep track of what changed, The YAML config editor also has the capability to compare the config file against the binary settings, and if there are differences, a pop-up occurs displaying the differences. This is an important feature for development and validation because those activities often involve tweaking firmware parameters. So in this example, first open a YAML or BSF file. Next, a pop-up will occur to query the user, yes or no, for the corresponding binary, for example, the fsp.fd file. If the binary file has different configuration data settings than the YAML or BSF file, the config editor will pop up a report showing the differences. The YAML config editor tool also has the capability to show the binary information from the binary file. This feature is similar as the previous BCT tool, whereby a FSP binary information can be rendered to tell which SoC it supports, along with the versions. After saving the config data to a binary image, the next step would be to use the updated FSP.fd file to build the platform bootloader with the updated values. Once the build completes, the new firmware image binary would get flashed into your system unit under test. In this case, we're just showing it with a Tiger Lake platform. Now let's look at the FSP mechanism for using runtime or dynamic configuration data. Per the Intel FSP spec, the UPD data can also be dynamically overridden by the bootloader during runtime in addition to static configuration. Let's discover how the POL bootloader would manage the UPD configuration dynamically. The configuration flow today has two parts, the FSP configuration and the BIOS setup menu configuration. For FSP configuration, the BIOS build process would generate FSP collaterals, such as FD and header files. The bootloader engineers would then consume these collaterals to enable the final boot solutions for end products. On the other hand, for BIOS setup menu configuration, the BIOS build process would generate human interface infrastructure-related files such as UNI, HFR, VFR, HPK files. These would produce forms and menus if an end user were to enter the BIOS setup. There's no UI to render BIOS configuration now without running the firmware and booting the platform and then entering into the setup menus. This gives the flexibility to have dynamic configuration settings, but there is a disadvantage because platform BIOS setup is very platform-centric and difficult to maintain and port to multiple platforms. There are also build time versus dynamic EDK2 PCDs. Build time would be similar to how the config data is updated using the open source YAML configuration editor discussed before, but also has the disadvantage of maintenance difficulty. The UPD data is organized as a structure. The temp RAM init, FSP memory init, and FSP silicon init API parameters include a pointer which can be initialized to point to each of the corresponding firmware volume UPD data structures. If this pointer is initialized to null when calling these APIs, the FSP will use the default built-in UPD configuration data in the respective FSP components. However, if the bootloader needs to update any of the UPD parameters, it is recommended to copy the whole UPD structure from the FSP component to memory. Update the parameters in the corresponding data structures with the desired data settings to the respective copy of the FSP data structures. Then initialize the UPD pointer to the address of the corresponding updated UPD structure. The FSP API will then use this data structure instead of the default configuration region data for platform initialization. The UPD data structure is a project-specific structure, and the integration guide will list further details of this structure with the platform specifics. The EDK2 bootloader also has a minimum platform architecture specification that has defined a method and policy for dynamically setting the UPD data configuration using libraries to pass the configuration data to and from the Intel FSP. The guidelines are that one silicon policy data structure is created per silicon module. The data structure should only contain data. Functions should not be used in silicon policy data, only data. When a silicon module installs this policy data, it should consider the most common usage as the default policy data. Therefore, a board module must only update non-default platform-specific values instead of all field for the data structure to update. This silicon code may expose the following libraries. One example is an API to initialize all policy data to the default value, based upon the current silicon. This is the silicon policy init lib. Another example is an API to tell silicon code that all policy data have been updated, and they are ready to consume. This is the silicon policy update lib. Using the silicon policy update library, the board package may reference a variety of sources to obtain the board-specific policy values. They could be the following: PCD database values, UEFI variables, binary blob or buffer, built-in C structure, or hardware information. This slide shows the data flow hierarchy for the Intel FSP policy data flow to and from the Intel FSP APIs from the minimum platform architecture spec. 1. The min platform package will have a hook to the family open board package for the silicon policy update function. Then the silicon policy update function will use platform configuration data from PCDs etc. to the UPD data structures. 2. The FSP wrapper will call the entry point of the FSP API. 3. The FSP API will use the UPD data structure initialized by the platform family open board package. 4. Upon completion of the FSP API, the platform family silicon package will call the silicon policy init function. When the policy configuration is completed, the platform family silicon package may indicate that the policy is configured with board-specific actions in the silicon policy done function. After policy configuration is completed, the board may indicate that the policy is configured with board-specific actions in the silicon policy done pre-memory API in silicon policy init lib. Take FSP policy in min platform package is an example shown on this slide. Therein we defined FSP policy init lib and FSP policy update lib. So there is an initialization function and an update function. 1. When the FSP wrapper wants to call memory init API, it calls update FSPM UPD data to get the UPD configuration. 2. Then FSPM policy init and FSPM policy update are invoked. 3. The message buffer FSPM UPD is updated with the corresponding platform-specific configuration settings from platform configuration data, for example, PCD settings. These setting defaults might be additionally configured through the platform's setup menus. 4. Then the FSP API will use the FSP UPD data, in this case for the memory init API. The platform silicon package provides the former PEI FSP policy init lib.c, and platform open board package provides the latter PEI FSP policy update lib.c. Here is the code on updating the silicon policy as shown per the diagram on the previous slide. This function will copy the contents of the values stored in PCD variables into the data structures that are consumed by the Intel FSP API for initializing memory. The example code is in Whiskey Lake Open Board Package FSP Wrapper Library PEI FSP Policy Update lib PEI SA Policy Update pre-memory.c. The following are summary points for the configuration data for the scalable Intel FSP. One of the most important features of the USF is having the capability to have customizable configurations based on a platform and/or customer's needs. The configuration region is specified as part of the Intel FSP spec and is a data structure called the Updatable Product Data, UPD, containing default parameters for FSP initialization. There are two methods for updating the Intel FSP configuration data. One is the static update using the YAML configuration editor. This will update the configuration data and the build of the bootloader will consume the new parameters. 2. Dynamically, a bootloader can produce a setup menu where a user can choose different default values of the UPD data. There are pros and cons to both methods. For the static configuration, using the YAML configuration editor produces a standard interface for customers to navigate different settings. while the dynamic method requires more maintenance on BIOS and firmware engineers for porting and platform dependencies. This concludes our dive into the USF Scalable Intel FSP configuration data parameter settings update methods.